Thanks for reminding. Okay, so we were just introducing the concept of the limit and the precise definition of the limit. And we don't want to spend forever on this. And, there are some tricky parts. So here is the precise definition. Let f be a function defined on some open interval that contains the number a, except perhaps at a itself, right? So we don't care what happens at the point. I keep repeating that, but that's an important thing, right? As far as the limit is concerned, what happens at the point is of no consequence. It's in the neighborhood that we're concerned. So we say that the limit of f of x as x approaches a is L, and we write that if for every epsilon greater than 0, that is, no matter how small, I mean, that's a general challenge, right? We're not thinking of epsilon as being a huge number, although like a billion is bigger than 0, right? So that epsilon could be a billion, but we're more interested in like a billionth, right? 1/1 billionth. So for every epsilon, no matter how small, we can find a delta sufficiently small so that if x is within delta of a, then f of x is within epsilon of L. Okay, and there's a little explore it here. I don't know, you may want to explore that, but in the interest of time, I'm going to move on. We also have one-sided limits, and it's just what you think, right? So I'm going to move on. Limit laws come into bear. So, we have the limit of the quotient is the quotient of the limits, right? So if you have a fairly complicated expression like this one, that's a rational function where the degree of the numerator equals the degree of the denominator. So it's going to have a horizontal asymptote of 3. In fact, that's another kind of limit that we will talk about, right? What about the limit as x goes to infinity of this function? It's going to approach 3, right? That's the whole idea of a horizontal asymptote, is that by taking x large enough, we can make f of x as close to 3 as we like. So that's a little bit different than, by taking x within delta of a. In this case, we say, in the case where we're looking at a horizontal asymptote, we'd say by taking x large enough, we can be sure that we're within epsilon of f of whatever, of 3 here, right? Is the horizontal asymptote, right? But also, what is f of 1 here? F of 1 is going to be, 7? Is that right? Yeah. 6 minus 8 is -2 plus 9 is 7, divided by 2 minus 1 is 1, 7 divided by 1 is 7, right? So we'd like to be able to say, how do we prove that the limit of f of x as x approaches 1 is 7? Well, we would use the limit laws here, right? And we could say, well, the limit of the quotient is the quotient of the limits, and compute the limit in the numerator separately from the limit in the denominator. And that might be easier than dealing with the whole thing at once. And so the limit of the sum is the sum of the limits. And they have a proof of that here, actually. And this is kind of interesting. What does it say? Let epsilon be given. So we're trying to prove that the limit of f of x plus g of x, if the limit of f of x is L and the limit of g of x is m as x approaches a, then the limit of the sum is the sum of the limits, right? And so we must let epsilon be given. So that's the challenge, right? You always start with a given epsilon, right? We must find a corresponding delta. So it's like a little game, I challenge you to beat this epsilon, and you find a delta that does it. And the trick to this is that oftentimes what we want is not the smallest delta, but the largest delta, right? So given a small value of epsilon, what is the largest value of delta that will still guarantee that if we're within delta of a, if x is within delta of a, then f of x plus g of x is within epsilon of L plus M.
Professor?
Yeah.
What do epsilon and delta stand for in these? You haven't explained that yet.
Oh, okay. They're just the standard, they're just Greek letters, so they're variables. But there's a special kind of variable that we use in this situation. I mean, special in the sense that we tend to think of them as small and positive, right? So notice that epsilon is greater than 0 and delta is greater than 0. So they're positive variables, and we're tending to think of them as small. That's it, right? So they're just variables, and epsilon is the challenge, and delta is the response to that challenge. So what value of delta can we choose here so that if x is within delta of a, so delta is like a distance, right? A small distance, and it's a distance from x to a, or it's an upper bound on that, right? So if x is within delta of a, then we want f of x plus g of x to be within epsilon of L plus M. We use the triangle inequality. What's the triangle inequality? Well, it's basically saying that the hypotenuse of a right triangle is a shortcut, right? To get from one acute angle of a right triangle to another acute angle of a right triangle, we could take the long way around by following the legs, but that's always going to be longer than following the hypotenuse. So the absolute value of f of x plus g of x minus L plus M, so that's the right side of this, that's the conclusion of this statement, right? Can I? No, okay. Oh.
The limit laws. As the preceding examples show, it is not always easy to
Can you hear that?
limit statements are through using the.
Yes.
Okay, that's interesting. All right, I didn't mean I didn't mean to, but yeah, it turns out if you click on these, you can get like a little blurb from your textbook. It'll talk to you. Who knew? Okay. It's interesting that you can hear it too, because probably because it's playing through my speaker and my mic picks up the speaker, but usually that's suppressed. I don't know what's going on. Anyway, what do I mean it's suppressed? Like when you speak, we'd have a feedback loop. If you spoke, it came out of my speaker and into my microphone, but they have a way of suppressing that feedback, right? It's a common problem that's been solved. Okay, so if we group the f of x minus L and the g of x minus M, then we can say the absolute value of that sum is less than the sum of absolute values, right? That's the triangle inequality. Okay, basically, yeah, here's a pure statement of the triangle inequality, right? I was going to make it larger, but apparently this one won't speak to you, which is just as well, I guess. Or maybe I need to kill that and then. Okay, all right. So if you want to brush up on the triangle inequality, they say see Appendix A. Okay, so if we make each of these less than epsilon over 2, then their sum will be less than epsilon, right? So that's the trick, is since epsilon over 2, if epsilon is positive, so is epsilon over 2, so we can find a delta 1 that will make this limit true and a delta 2 that will make that other limit true. And if we take delta to be the smaller of those things, then both of those inequalities will be assured, that f of x minus L will be less than epsilon over 2 and g of x minus M will be less than epsilon over 2. We get what we want. Okay, the other kind of definition are limits at infinity. So if you have a vertical asymptote, that's what's going on here. As x approaches a point on the x-axis, f of x approaches infinity. That means we got a vertical asymptote, right? And that means that for every positive number m, there is a positive number delta. So notice m here, instead of an epsilon, we have an m, right? And that's because we want to say we can always make x large enough. I'm sorry, no matter how large m is, we can pick an interval of radius delta around a, so that if x is in that interval, then f of x is bigger than m. That will assure that f of x goes to infinity. No matter how large we choose m, we can always find an interval around the point a, so that if x is in that interval, f of x is bigger than m. This takes a little while to absorb, so if you're feeling a little confused, here's a picture that's normal. Right, so here's the challenge m. By taking a small enough band around a, I can be sure that if x is in this interval, then f of x is above m. And I can always do that no matter how big m is, right? Because that's just the nature of the beast here. So given any horizontal line, right? So that's just saying what I said. Okay. So here's an example of using that. Okay. We want to prove that as x goes to 0, 1 over x squared goes to infinity. It's about the simplest example you could pick, right? And given any m, no matter how large, we want 1 over x squared to be bigger than m. Well, so they do a little algebra, right? And so is it clear that these statements are equivalent? M is a positive number, right? So in the case where m is positive with an inequality like that, you can say if the left side is bigger than the right side, which is positive, then the reciprocal of the left side is smaller than the reciprocal of the right side. Right? The reciprocal of a large number is a small number, and the reciprocal of a larger number is a smaller number. Yeah? And then you solve for x by taking the positive square root, or actually that's the absolute value of x, right? Which is the same as x minus 0, the distance from x to 0, right? And so by choosing epsilon equal to the reciprocal of the square root of m, we can be assured, by picking delta, did I say epsilon? I meant delta. By picking delta at most the reciprocal of the positive square root of m, we can be assured that the reciprocal of x squared will be greater than m, right? Because of the sequence of equivalent inequalities. And this is the way it works generally. You start with the challenge and work backwards towards the response. All right, we'll see how to do that with a few examples. Okay, so and the definition for negative infinity is the same. You just no matter how negative, right? By like negative a billion, right? So I don't want to say how small, because we tend to think of small as near 0. No, this is the kind of small that's near negative infinity, right? Okay, and so let's move on. Are we ready for exercises? Yes, we are. So here's a good one. What value of delta for this graph will assure that f of x is within 0.2 of 1? And if delta were 0.3, that wouldn't work, because you'd have a value like 1.2 where the output is not within the epsilon band, right? Is it clear what I mean by the epsilon band? That's this interval of radius 0.2 centered at 1, right? So if epsilon is 0.2, then we want f of x to be within 0.2 of 1, which means it's between 0.8 and 1.2. So what interval around 1 on the horizontal axis will assure that the output, all right? So you would just want to basically, you want to choose the smallest. This 0.7 is not good, right? I mean, it's good on the left, but if we were to pick that same distance on the right, we'd be at 1.3, where you can see the function values are outside that epsilon band, right? So to be sure within the epsilon band, we'd pick a delta of 0.1 here. All right, that's all I'm going to say about that. What value of d will so here the epsilon is a challenge, right? So we get this interval of radius. See, I call it a radius. I know it's not a circle, but it's like a one-dimensional circle. When you get into higher dimensions, you do think of circles and balls. And so that's where that radius language comes from. Maybe I shouldn't use it. Yeah, interval of radius 0.5 centered at 2. Does that make sense? It's centered at 2. So you go up 0.5 and down 0.5 from 2. And you have this epsilon band around 2. Maybe, yeah, band is better than ball.
Yeah, that makes more sense.
Yeah, so you've got this band of radius 0.5 centered at 2, which if you look at what the x values are on the left and the right, so we want to prove that the limit as x approaches 3 is equal to 2, and we have the challenge epsilon equals 2. What delta will meet that challenge? And now you see the smaller distances on the left, so you'd have to pick delta equal to 0.4 here, right? If you went more than 0.4 to the left, you'd be outside of the epsilon band, right? So you want the largest delta that will work here is delta equals 0.4. Of course, you could pick delta smaller, right? And that would also meet the challenge. But oftentimes what we're interested in is what is the largest delta that will meet the challenge for a small epsilon?
Professor,
Yeah.
Is delta always on the x-axis and whatever the other, what's
Epsilon?
epsilon always on the y-axis?
You know, I never say always, but in this case, I'm tempted to, because yeah, so we're thinking y is a function of x, right? I suppose if we were thinking x
Right.
is a function of y, then we would have to reverse which is which, right? But if y is a function of x, and x is the horizontal axis, and y is the vertical axis, then the challenge is on the output, and the response is on the input. So the output is the y-axis, so that's the challenge, that's epsilon. The response to the challenge is on the input. What range of inputs will assure that the output is within 0.5 of 2? And if I had a range of inputs from 2.2 to 3.8, that would be a radius of, well, that would be a distance 0.8 from 3, right? And that would be too large, because on the left side, you'd have some function values which are more than 0.5 away from 2. Okay. So use the graph, and again, they're using the graph, right? So let's get to ones where we're, use a graph to find a number delta. Okay, I suppose we could talk about that. So this is the function which is the square root of x squared plus 5. I'm kind of tempted to go to a GeoGebra window, right? Yeah, let me bring this back over here to where I am. Oh, yeah, let me bring, you're not, oh, you can't see my tabs. I shouldn't show my tabs, right? There, okay. Yeah, then I get more of a window anyway, right? Okay. So I'm going to bring this over to here. Okay. Oh, that's it. Am I good now? So I got this. This is, yeah, and then I got left here. Oh, that's the wrong one. Oh, but this is, oh, sorry. I've got my tabs all screwed up here. So this is where we are in the book. And yeah, okay, that's good. This is our, okay, and then this. All right, so what was our function was the square root of x squared plus 5, as I recall. Was it x squared plus, squared? Oh, that's odd. Squared, there we go. Notice that the positive square root of x squared is the absolute value of x. Does that make sense? Yeah, if x is negative, when you square it, you get a positive, and then you take the positive square root, that's the absolute value, right? So, but we want +5, which is going to give it a little bit of a curve, right? And we want to look at the interval around, so can I say, oh, well, let me go back to the book, and it says 0.3. So we get a band of 0.3 around the function value. And the function value at 2 is going to be 3, right? So, yeah, so we want to be.
Could you elaborate on that? What do you mean by a band of 0.3?
A band of, I call it a radius of 0.3, sorry. So you see that's this value on the right side, right? So that's our epsilon, right? That's the challenge. So we have an interval, so we want to prove that the limit as f of x goes to 2 is 3, and the function is the square root of x squared plus 5, right? And at 2, that's going to be 3. So, so if we want the distance from f of x to 3 to be less than 0.3, that means it's f of x is going to be between 2.7 and 3.3. So let's draw the interval, or let's draw the line y equals 2.7, and let's also draw the line y equals 3.3. And that's what I call the epsilon band around 3. Can we,
Professor, the function is supposed to have a -3 after the root.
no. Can I write on? I mean, yeah, I appreciate your comment, but and I'm glad you asked that, because that's probably a point of some common confusion. So I need to bring up GIMP if I'm going to do this.
Oh, I see what you mean. The distance from f of x to 3. Never mind.
Yeah, right. Yeah. I'm not sure what I did there, but I tried doing it again. Okay, there it is. The computer went black for a second. That was scary. Okay. Oh, so now you get to see my GIMP. I'm not sure why. Oh, I think it's because, yeah, I need to open file, open recent that. So this allows me to write on a blank screen. Although I see I have a big black band there, which is, okay, that went away. All right, good. So I got a surface to write. Oh, but I haven't turned this on. Yeah, this is going to involve some work. I forgot that I rebooted my computer. Okay, so I can't write on here. I suppose I could make, yeah, actually I can, yeah, we could make a little comment here, right? Oh, where's the text box? Is it in here? Oh, here, text. So this is saying that, I'm going to put this in LaTeX. So I'm going to say absolute value, does that work? Of f of x. Well, first of all, I want to say f of x equals the square root of, let's see, I'm never sure which notation to use. X squared plus 5, right? And I want to say the absolute value of f of x minus f of 2 is less than 0.3. I want to make that a LaTeX formula. It's not allowing that. Oh, okay. It doesn't know the absolute value. Okay, that's fine. I can just put in these bars here like this, right? Okay, and I think I want to put in a, yeah. Okay, and for some reason I have an S there. Okay. I can say enter now. Oop, that's not what I wanted. How do I? How do I enter that? I'm not sure. Maybe I'm missing a box at the bottom. Oh, I have to say okay. All right. So, oh, square root needs a little slash before it. Sorry. Oh, and now square root, I think I have to put it in curly braces. Yeah, well, you should learn LaTeX. Yeah, all right. So LaTeX is a language invented by Donald Knuth for making pretty math expressions. And if you pursue math and science as a career, eventually you're going to have to come to terms with it. Okay, so here's our function. And we want to assure that f of x minus f of 2 is less than 0.3. That is, we're somewhere in this band, right? Because what's f of 2? F of 2 is 3, right? So f of x minus 3, that is, we're in this interval between 2.7 and 3.3. Okay, so what interval around 2 will guarantee that? Well, what value of f of x will get us to 3.3? Do we need to do some pencil and paper? Well, let's do some pencil and paper, probably just because we need to anyway. Okay, so our function is f of x equals the positive square root of x squared plus 5. And we want to say that the limit as x approaches 2 of f of x is equal to 3. So one way to say that is to say, given the challenge epsilon equals 0.3, or let's say, what is the largest delta that will, because you always choose delta to be like a billionth or something ridiculously small and just hope that's good enough, right? What is the largest delta that will assure that if x is within delta of 2, then f of x is within 0.3, or epsilon, right? So our epsilon is 0.3, is within 0.3 of 3. All right, and so in order to find that, it might be helpful to solve this equation, right? F of x equals 3.3. That's the extreme on one side, right? And so that says x squared plus 5 is equal to 3.3. Oh no, we have to square that. X squared plus 5 equals 10. Oh God, I can't do it in my head. So this is 99, 99. Yeah, 9, 8. Right, 10.89, right? So subtract 5 and take square roots. Now, do we want positive square roots or negative square roots? I think we want positive, right? Because we're in a neighborhood of 3, right? So we're not near negative numbers. We're near 3, right? So what's the positive square root of 5.89? on a Monday? Well, you know how to do this, right? You say 2, you get 4, you subtract 1, you double that, and you say 40 what times what? I think that's 44, and so 16, 7, so you subtract, you get 3. Do you do it this way? Is this the way you find square roots? I think maybe Jonathan saw this last semester. So you double that 4, you get 480 what times what is the largest number less than that, and it's going to be well, approximately 3, right? So this is approximately 2.43. Okay, so that's the extreme on one side. How about on the other side? All right, well, we want f of x equal to 2.7 if you're going to be, you know, at the other extreme, right? So x squared plus 5 equals 2.7. Now the square of 2.7, I can't do that either. 2.7, is it 7.29? Could be, huh? Yeah, 7.29. So x squared plus 5 is 7.29. X squared is 2.29. And what does that mean about x? Well, we want the square root of 2.29, so we'd go 1. This is how they taught you to do square roots, right? 20.
I've never seen that before.
They made me learn this in elementary school. So 5, and so 125, we subtract, we get a 4. So 300 and what, that's going to be a 1. So this is approximately 1.51. What? Sorry, 1.51. And shall we see that that's true? Let's go back to our GeoGebra window. I think we can actually just click on these points, right? And it'll compute it for us. Right, the intersection there and the intersection there. And what do we see? 1.51, yeah, that's what I just computed. And the other one is 2.43, yeah, that's what I computed. So which one of those is closer to 2? Well, 2.43 is 0.43 bigger, and 1.51 is 0.49 smaller. So it's the 2.43 that's they're pretty close, right? But so you should pick the smaller of those as your delta, right? So we should pick. I would say, can we have another text window here?
Professor, I have a quick question. Why did you choose 2.7 and 3.3?
Because that was the challenge, right? If you go back to the text, they said we want f of x to be within 0.3 of 3. So what is the farthest away on the upper side you could go? Well, 3.3 more than 3.
That makes sense.
The farthest away on the other side you could go is 0.3 less than 3.
So it just depends on what's given and whatever the challenge is.
So those are like the extremes of our interval, right? So I want to say, you know, if, and I guess I'll just write here absolute value of x minus 2 is less than 0.41, was it? Sorry, 4.3. Then absolute value of f of x minus f of 2, and I don't know if I can make this pretty type, less than 0.3. And that does the trick, right? So choose delta equal to 0.43. That'll be the largest delta that will do the trick. And even that one is a little bit, yeah, I think that's actually smaller than the square root. Yeah, so that would work. If we had rounded up, that would be a mistake, right? Because then we're going to include some points outside the epsilon band. Right, and so I can also draw the delta band here, which is going to be x equals, I'm sorry, what is it? 2.43, right? And the other one is going to be x equals 1.57. And notice that that's a little bit, you know, that's an interval centered on 2, right? But it's actually narrower. It doesn't go to the extreme of the point A, because if it did, we'd have values that are outside the epsilon band.
I thought it was supposed to be 1.51.
Yeah, right. So this is an interval from 2 minus 0.43 to 2 plus 0.43. So that's an interval centered on 2. And if we're inside this interval, then f of x is going to be inside the epsilon band, right? If we were to choose a larger interval, then over here we'd have trouble, right? Because we'd get some values of f, the output values that are above 3.3. So you got to just sort of pick the smaller of those two distances. And that'll be the largest delta that'll work. Yeah, inequality is tough stuff sometimes, yeah. I'm wondering, is there a way of saving this? I think I can save it locally. That way we can pick this up again if we want. I don't know. It's probably not worth saving. Yeah.
When we finish with this example, could we go back to the very first one? I'm still feeling pretty lost on that.
Okay. So the one with the graphing, right?
Yeah, I don't even know what question to ask about where I'm lost. I'm just completely and utterly lost.
Uh-huh. Yeah, that's normal.
Same here.
I hate to say it. But so you're talking about like this very first example here.
Yeah.
Right, is it clear why we had to choose delta equal 0.1, that 0.3 was too big?
Nothing is clear about anything.
Okay, so what interval, I guess what value of delta will assure that if x is within delta of 1, then f of x is within 0.2 of 1? Notice f of 1 is equal to 1, so the input is equal to the output. All right, so you look at the range of output values between 0.8 and 0.2, and you can see they come from a range of input values between 0.7 and 1.1. So we want an interval centered on 1, which goes, the same distance to the left of 1 as to the right of 1 on the horizontal axis, right? So that if we're within that interval, then the output is within 0.8 and 1.2. So if we were to go from, say, 0.7 to 1.3, then you would see output values below 0.8, right? Which is too far away from 1. Kind of unfortunate that they have the same input and output, right? Maybe this one is maybe a little bit better, right? So here the challenge is 0.5. That's our epsilon, right?
Professor.
Yeah.
Would it be possible to like explain like just in simplistic terms what I understand what some of those symbols mean, but how they all come together and what they mean in this context for someone that has never taken calculus before, or doesn't understand this part of it. I guess the way the question is being asked and how that translates to what you're doing, I guess is what I'm trying to get at. These symbols here, the symbols right there from the question, like everybody, like Jonathan said, I'm lost, and I don't understand. I'm not following, I guess, is my point.
Okay, well, let's start with this expression here. Okay, this compound inequality. And notice they're using D instead of delta. That's odd. I think maybe that's a typo, because they are talking about a delta up here. Is that confusing? That is confusing, huh? They meant to put a delta here. There seem to be a lot of typos in this book, I gotta say. I don't know. I've come across quite a few and haven't gotten into chapter 3 even. Well, but so delta is the Greek letter D, so it's kind of not a surprising mistake to make, but I didn't notice it even the first time I looked at it. So imagine that D is a delta, right? So what that inequality says is just kind of ignore the greater than 0 part, because that's clear. If x is not 3, then the absolute value must be bigger than 0, right? And we don't care what happens at 3, right? That's at the point. We want the neighborhood of the point. So what this inequality says is that the distance from x to 3, that's this distance on the x-axis, right, is less than d, or delta, right? So if delta were 0.8, then x could be any number between 2.2 and 3.8, right? And you would be within 0.8 of 3, right? 0.8 to the right of 3 and 0.8 to the left of 3. That's that interval centered at 3. I like to say a radius 0.8, but that's the value of delta, right? So, but notice here that this interval is not, is narrower on the left than it is on the right. Well, that's because we're starting with the challenge, right? So this interval on the y-axis describes the second inequality that says f of x is within 0.5 of 2, right? So it's no more than 0.5 bigger than 2 and no less than 0.5 less than 2. It's between 1.5 and 2.5. Right, so that's the challenge. So we look at what are the extremes on the x-axis that will allow that. And you can see it's the interval from 2.6 to 3.8. Now 2.6 is 0.4 less than 3, and 3.8 is 0.8 bigger than 3. So if we were to choose delta equal 0.8, we'd be going from 3.2 to 3.8, and that would give us input x values that would be outside of that delta epsilon band, right, between 1.5 and 2.5. So you want to pick the smaller one. So the smaller point is the point on the x-axis that's closer to 3 is the 2.6, and that's within 0.4 of 3. So delta would be 0.4 here. Does that help? So you have the challenge. It's like a game, right? You're given a challenge, and you have to have a response that will be sure to meet the challenge. And you can draw a picture like this, and then just pick the smaller distance from 3, which in this case is 0.4.
So they always give you the output, or for these in particular, they give you the output and they want you to find the input that will give you that output.
Yeah, there will be. So what range of inputs will guarantee, and it has to be a range of inputs centered at 3, right? And notice that range is not centered at 3 because it's going from 2.6 to 3.8, right? So it's not centered. You want it to be centered. So what you do is you just bring in that 3.8 down to 3.4, then you have an interval that's centered at 3, And you can be sure that if x is within the interval from 2.6 to 3.4, then f of x is within 0.5 of 2. It'll never get, more than maybe 0.4 bigger than 2, right? Because you'll be a little bit narrow, but you've met the challenge. All right, well, let's try some with variables. And I'm gonna go to pencil and paper because I think they kind of skipped over some important examples here that are simpler than this cubic example here. Yeah, I guess you can use the graph again. They notice they do have a picture. I don't know. You want to do number 7? We can do number 7 and then maybe talk about some simpler ones, right? So this is a cubic polynomial. So if I go to GeoGebra, I wasn't able to save this, huh? Do I want to save it? I don't know. Seems like maybe I'm not seeing everything I want to see because I'm not seeing the whole thing. Yeah, I guess I'll just, I can make a new one. And drag it over. Okay. So what's our function? Was x cubed plus something plus something? X cubed minus 3x plus 4. And stick with it. I mean, be patient with yourself. This is a notoriously difficult part of calculus. It's so difficult that oftentimes it just gets dropped. But I feel irresponsible just dropping it, right? Because it's important stuff. So it's the precise definition of the limit. The limit is the foundation of all calculus, right? So why not at least try to do it right? So x cubed minus 3x plus 4. Okay, so here's our function x cubed minus 3x plus 4. I believe that's it. Yeah. And what do we want to show? We want to show the limit as x approaches 2 is equal to 6. Is that true? What's the point 2 comma f of 2? Oh, that's right there. Okay, that's that point, right? So we want to show that, and intuitively it's obvious, right? So this is not about the intuition. This is about the precise definition, right? So we want to sort of zoom in on the x-axis. And what was our challenge? The epsilon value here. So epsilon is 0.2 first. Okay. So let's go to 0.2. So this is the line y equals 6.2. That's going to be the upper range of our epsilon band. And y equals 5.8 is going to be the lower range of our epsilon band, right? So we want to pick our interval around 2 on the x-axis so we can be sure that if we're in this interval around centered at 2, right? So a little bit to the left of 2, the same distance to the right of 2. If we're in that delta band, then our function values are guaranteed to be within the epsilon band. I kind of picture, the trombones and the tubas marching down Main Street when I say this, but that doesn't help.
And to set up the equation for that, we set this x cubed minus 3x plus 4 equal to 0.2?
No, but you're close, right? We want to say what are the coordinates? So let's go ahead and plot those points, right? So
we set it to the y value.
Yeah. Okay. So
okay, cool.
Yeah, right. So we want f of x. We want to solve this equation. So in fact, GeoGebra has a little solver. It seems kind of cheesy. Do we really need it here? Kind of, right? Because this is a cubic equation and it doesn't have an obvious solution, right? So we want to solve f of x equal to what was 6.2? Oh, that's 3.2. 6.2. I want to solve that for x. Boom, it found nothing. Okay. Why didn't it solve it? Instead it made, well, let's see, if I say solve, it'll show you the solve equation. Okay, so you don't have to say what you're solving it for. Okay, you just give it an equation. All right, f of x equals 6.2. Illegal multiplication.
Does it need to be 6.2 equals x to the third minus 3x plus 4?
Yeah, I suppose, but I mean, it should know that f of x is, right? Why should it have a hard time with that? And then what is this slider bar? That's crazy. It's misbehaving, if you ask me. So, okay, let's try it. Let's take your suggestion. Solve x cubed minus 3x plus 4 equal, oh, I mean the exponent. Minus 3x plus 4 equals 6.2. Boom. Okay, it's just not doing it, huh? It was too hard for little old GeoGebra. Let me look at that syntax again. Solve. Oh, so that's an ODE. That's an ordinary differential equation. That's not what we want, right? And what did I say? Maybe it's because I put curly braces or something. So this is f of x equals 6.2. Oh. Okay, this time it did it. I don't know what I was doing differently before. I think maybe I was using curly braces instead of parentheses. Yeah. All right. And let's go here and then here and say we want more decimal places. Okay, so we can see 2.02219, right? Okay, and then what about on the other side? What do you expect anyway? Do you expect it to be closer, the x value of x closer to 2 or farther? I think farther, right? Because this thing is rising more steeply as x increases. And so the one on the left is going to be farther away than the one on the right. Does that seem intuitively correct? Okay, I need to say solve parentheses f of x equals 5.8. And it gives me 3 solutions, right? So why 3 solutions? Well, look, if this one intersects the function at 2 other places. We don't care about these places, right? We're interested in only over here, where we see one of the solutions is 1.9. So let me draw that vertical line. X equals 1.97744. Okay, so there's that vertical line. And the other vertical line is x equals 2.0219. Okay, so this is the region we're interested in here, right? I'm kind of trying to zoom in on this. It's slow going, this zooming. Right? So is that interval centered around 2? Not quite, right? You see the distance on the right? It's not obvious, is it? You have to look kind of very carefully at it. And we'll just look at the numbers, right? So which of these 2 numbers is closer to 2? And this is like 0.0225. This is 0.0219, right? So this one, the one on the left, is farther away, right? So I should choose my delta band to be small. I would choose delta here. Can I write the text? So I'm going to say text. If space, then absolute value of x minus 2, absolute value is less than 0.0219, right? That's the smaller one, right? Next. Then space here and there, right? Absolute value of f of x minus 6 is less than 0.2. All right, so that's a statement I would write for this. Does it fit in here? All right, so this is saying if, there's no good place to put it, is there? If x is within 0.0219 of 2, then f of x is within 0.2 of 6, right? That's what this is telling us. And it's a pretty close call, right? Because it's almost linear there, right? And so if it's linear, then it's the same on both sides, right? But okay. And again, we had to sort of go to the graph and do linear analysis or do numerical analysis in order to get that. Let's try a linear one with just pencil and paper. And let's try one where it's not possible, right? So we can see the pathology of this, right? So how about a general situation? I can just sort of say, f of x is mx, well, that's mx plus b. Prove that the limit as x approaches a of f of x is, you just plug in the x equals a, right? Okay, so the challenge, I'm just going to use a general epsilon now. I'm going to say, we wish to show that for any epsilon greater than 0, we can find, and let me emphasize here, delta is going to be a function of epsilon, right? So you're going to have to find an expression of delta in terms of epsilon in order to guarantee this, right, in general, right? So we've been using, fixed values for epsilon, but this is an easy enough case to where I think it'll allow us to transition over into the more general case, right? In fact, in the last one, we were supposed to also do 0.1, right? Didn't seem worth repeating all that just for another number. So let's jump to the variable, right? We wish we can find delta so that if x is within delta of a, then f of x is within epsilon of ma plus b. All right, so this is f of x minus L, right? This is our L, the value of the limit. And I just found it by plugging, this is our value of L. I found it just by plugging in, x equals a. Okay, so we start out with this. And we want, okay, so this is, and substitute mx plus b. All right, so I just substituted the function for f of x. Now what happens? Well, the b's cancel out. Oh, that's nice. And the remaining terms have a common factor of m, right? So this is equivalent to saying, so I'm writing a sequence of equivalent inequalities here, right? That I'm going to assume that m is positive. Is that okay? I don't think it matters much. And this way it comes out very quickly, right? So what should our delta be? So these are all equivalent inequalities, right? So we sort of work backwards from what we want to what will give us what we want, right? So if x is within epsilon over m of a, then these are all equivalent, right? F of x is within epsilon of ma plus b, right? So delta equals epsilon over m will do the trick. And it is just kind of like a stupid pet trick in the end. Well, okay, so now, right, with more curvy kind of things, it can be trickier, right? Like what kind of more curvy things? Well, how about a square? Should we do another one with a square? And then maybe we'll look at some web assigned problems to see what horrors await us there. Any questions about anything? Yeah, this is 2.4. Yeah, I was doing an exercise from the book. That's right. Okay. Okay, so how about f of x? And now I'll use some numbers instead of parameters. On the last one, I used parameters m and b just because, you know, it seemed too easy just to use numbers. And, you know, in general, you can use parameters, right? That worked out pretty neatly. The b dropped out, right? So if x is within epsilon over m of a, then f of x is within epsilon, right? Because all these equations are equivalent, right? So this inequality assures us of that inequality, which is what we want. We want this one, and this one is equivalent to that one, and so we get it, right? Now with this square, things are a little bit trickier. Okay, so how about the limit of x, about 4 minus x squared as x approaches 1 is equal to 3. So we want to prove that, right? I'm sorry. I'll just turn this thing upside down so I can. So we want to prove, I misstated the problem, that the limit as x approaches 1 of 4 minus x squared equals 3. And clearly this is true, right? Intuitively, this is a smooth, continuous curve. There's no troubles. You can just take that 1 and plop it right in there. 4 minus 1 squared is 3. Okay, so so we want to prove that is given any epsilon greater than 0, no matter how small, is generally the implied phrase there, right? We seek delta such that if x is within delta of 1, then should I put an if? Then f of x is within epsilon of 3. So again, I'm going to start out with my goal and work backwards towards what's going to get me there, or I'll try. I'll do the best I can. So I'm going to substitute again, right? So f of x is 4 minus x squared. I'm just going to substitute that in there. 4 minus x squared minus 3. We want that to be less than epsilon. So we want to work towards, you know, can we get a value of delta? So, you know, x, something like this, right? X minus 1 Okay, well, 4 minus 3 is 1, right? So the equivalent inequality here is 1 minus x squared, just simplifying what's inside the absolute value, right? And I'm going to do a little something here. X squared minus 1. Is that allowed? Can you do that? Is that equivalent? Sure, it's an absolute value, right? So if you substitute the opposite thing, you got the same thing. Because I mean, after taking the absolute value, right? So the absolute value of 3 is the same as the absolute value of -3, and reversing the difference just gives you the opposite. And then you take the absolute value, you get the same thing, right? So now I'm going to factor, right? Because I can. And it's going to be x plus 1 times x minus 1 is less than, oh, look at that. There's my x minus 1, right? That's what I want inside the absolute value. So I have this extra. So can I pull that out? Now we can't just divide both sides by the absolute value of x plus 1, right? Because then we'd have, x in terms of x, or delta in terms of x. We don't want it in terms of x. We want it just in terms of epsilon. Is this getting any better? Or? Yeah. So maybe drawing a picture would help here. So what does my picture look like? Well, this is a parabola with a vertex at 0, 4, passing through 1, 3, right? So here's, and I have, intercept at 2, huh? So here's the x-axis. These are perfectly evenly spaced hash marks on the y-axis. And we have a vertex here, and we're passing through this point here and this point here. So it's a parabola going down like that, right? So what is our limiting value is 3, right? So the epsilon band is going to look like this. The trombones and the cellos. Do we see cellos in the marching band? So can you see that there is, we can obviously make a very small tight band around 1, and then all our function values will be within that epsilon band. But we want the largest one, right? And notice that it's dropping off to the right faster than it is on the left. And so probably it's the one on the right that's going to give us the tighter bound, and that'll give us the largest delta that will work, right? So this, what are these points? This is 3 plus epsilon up here, and this is 3 minus epsilon down there. That's the extremes of the epsilon band, top and bottom, right? So now I'm going to say that if x is near 1, let's say if x is within 1 of 1, then x plus 1, the absolute value of x plus 1 is less than 3. So that's kind of a subtle observation you need to make at this stage, or that is helpful to make at this stage, right? So if x is within 1 of 1, sorry, it's the same number, then x is between 0 and 2, and the absolute value of x plus 1 is between 1 and 3, right? So the largest it can be is 3. Okay. So I'm going to say then that, for fairly large delta, I mean, delta 1 is fairly large, right? We can be sure that, that this is less than, so if x is within, I'm just repeating that, 1 of 1, then absolute value of x plus 1 times absolute value of x minus 1 is less than 3 times absolute value of x minus 1. Is that agreeable? Right, so this is bigger than that if x is within 1 of 1, right? Because x is between 1 and 3 then. Okay, and so if we assure that that's less than epsilon, then this will be less than epsilon, right? Transitivity of inequality. Okay, and that's equivalent to saying x minus 1 is less than epsilon over 3. And so there's my delta. Actually, what we say is delta equal to the maximum of 1 and epsilon over 3, which if epsilon is equal to 3, well, that's a pretty large challenge, right? Typically, we make, oh, sorry, did I mean minimum. The other maximum. Yeah. So if epsilon is equal to 4, then, well, delta equals 1 will do the job, right? So, but we're not interested in a large epsilon. We're interested in small epsilon. All right, and if you want to see this argument written up in a nice way, our book doesn't seem to have it written up in a very nice way, honestly. So let's go to here. I put in a little resources for, and here's a little web page where this is the University of San Francisco, and it's actually their early transcendentals for calculus and social sciences, whatever. Huh? We don't have that course. Oh, I'm sorry, I'm not showing you the. So how did I get here? I missed hitting the. Shall we go back? So I went to our modules for the module for this week, and I hit this resources for limits. There's only one link in here now. I may add more as time goes on, right? But you know, I want to steer you clear of that bad Khan Academy where a lot of people find themselves wading through the muck. And you know, I'll try to curate some nice links for you. I think this is a pretty good one. So the precise definition for a limit, and they give you that precise definition here, and they give you some nice examples. This is what I like about this, right? And then they show you the solution, right? And so here's a linear one. So notice that this is a line of slope 1. In that case, m is 1 and delta equals epsilon will work, right? And so that's just like our first example, only a specific case of it, right? So here's one that's kind of similar to what we just did. And it's got all of what we just talked about, right? So whichever is smaller. So here he ends up picking the minimum of epsilon over 5 and 1, whichever one is smaller. So if epsilon is huge, well, delta equals 1 will work, right? But it's not much of a challenge. If epsilon gets to be smaller, then choose delta equal to epsilon over 5. And then if x is within epsilon over 5 of 2, then f of x is within epsilon of 0. Oh, I'm sorry, of 4, sorry. Yeah. All right, you can read those over. Let's take a gander and see how it's going to be with the web assign. How bad can it get? So do we have 2.4 in here? I think maybe we don't, right? I need to call this up here and schedule it for you guys. And I'm going to drag it over into week 4. And there's another one here.
We can already see it.
Oh, really? Huh, okay. That's interesting. I don't recall doing that. Or maybe you're looking at 6198. I don't. You don't get the 6198, do you? I don't know. Anyway, so if we go then back home, you can see I've got two sections here, right? So now we see the 2.4 is not here. I don't see it. You see it, but I don't. Okay. So let me try reloading this.
We have access to both 2.3 and 2.4 on
Oh,
our end.
Yeah.
There's a button there that says more.
Oh, more. Thank you.
Now we have two.
Now you have
2.4.
two. Okay, let me delete that one. Okay, so okay, you do have two, huh? So I think this is the one I just added, right? Trash? No, just for oh, well, that's odd. Okay. Let's just go home here and we'll figure out what to do about that later. So have you already been working on one of these? More. That's irritating. 2.4 limits. And then there's another.
I haven't. I was going to start it today.
Yeah, so 2.4 is due on the 23rd, which is Wednesday, and this one is due on the 20th. Well, let's see if maybe this is.
The one you originally posted was the one due on Thursday.
Yeah. Okay. And oh, you got a lot of problems here. Has anybody started this yet? Because I can just delete this one if nobody started it. It's kind of annoying that and the other one I think had fewer problems, and I think that would probably be just fine, right? So I'm going to say, yeah, okay, fine, if that's a disaster. This assignment will no longer be displayed. Okay, so back to my assignments. All right. So here we have this one. Okay, let's formal definition of the. Okay, so this one only has 10 problems. I think that's plenty. So I'm glad. Yeah, right. Okay, so I think what I want to do is preview the assignment, or I think I can just go back to here and say view. Does that work? So 2.4, I have to say more. And then view, and does that bring up a window which is now invisible to us? Yes, it does. So I have to bring up another window to view this here, which is not a problem, I guess. So add a window, capture, which is going to be that, and let's see if I can capture. Oh, I have to get a choice. Yeah, okay. I'm going to say okay for that, and then make this bigger. Oh, and okay. So, oh, this is just that same problem, right? So this should be good if we say delta equals 0.1, right? That's so if we're in this band from 0.9, if x is between 0.9 and 1.1, then f of x will be between 0.8 and 1.2. Actually, it'll never get up to 1.2, but that's okay, right? We just want to be sure that it's somewhere in that interval. It doesn't have to cover the whole interval, just has to be inside of it. So in fact, I could choose, 0.99 to 1.01, and that would be even better, I suppose. But usually the game we play is what's the largest delta that will do the job? And in this case, that's 0.1. How about here? Well, oh, I see. They want us to actually find these function values. So that what x value will give us the square root of x is 1.6. Well, 2.56. Right, the square root of 2.56 is 1.6. Oh, I see. They want a value of delta, though, right? So they have these question marks. I wish they wouldn't have that. Yeah. So, I mean, we kind of want to find these values. So I'm not going to find these values, but that's not the answer, right? I'm just having them here to look at, so I can write there. So what number has a square root of 2.4? Well, the square of 2.4 is 5.76, I want to say. Is that right? I think so, yeah. 5.76.
Yeah, that's right.
So which of those is closer to 4? I think the 2.56 is only 1.44 away, right? Whereas 5.76 is 1.76 away, right? So the closer one is 1.44 away. 4 minus 1.44 is 2.56, and so you would choose delta equal to 1.44. That will assure you that you're within. So if x is between 5.76 and 5.44, then f of x will be certain to be within 1.6 and 2.4. Actually, it'll never get up to 2.4, right? Because you'll stop short of that, but you'll be contained inside that interval. Well, let's leave a couple for you to do. A graphing calculator is recommended here. Oh, okay. So, so this is the other kind of limit. We haven't talked about this one except for the exposition in the text, right? So we know that the limit as x approaches pi of cosecant squared is infinity, because cosecant is the reciprocal of sine, and sine of pi is 0, and it's squared, so it's going to be, you know, approaching 1 over a small positive number, right? Illustrate the precise definition of an infinite limit by finding the values of delta that correspond to the following. And I think maybe we need some pencil and paper for this, huh? Okay, so I will switch over to pencil and paper by doing this. Okay, and let me look at the function values. So what is the function? So we have a limit as x approaches pi of cosecant squared. Okay, not my favorite function in the world. I prefer secant to cosecant, but it's just a quirky preference. Okay, and so what does the graph of cosecant squared look like? Well, it's going to have zeros at 0, vertical asymptotes at 0 and pi and 2 pi, right? And at pi over 2, sine of pi over 2 is 1, and so the reciprocal of 1 is 1, and the square of the reciprocal of 1 is 1, so you're going to have a minimum value there, right? So it follows these asymptotes, and then it's periodic like that, right? Okay, so that's what our function looks like, and we want the limit. So by taking x close enough to pi, we can make f of x as large as we like. That's the idea here, right? So we want to say we seek delta so that if x minus pi is less than delta, then f of x is greater than m for a given n. Shall I say no matter how large? So we can make m, usually you start out with, say, given m, maybe I should say that. given m, you seek delta so that if x is within delta of pi, then f of x is bigger than m. All right, so let's start out with our challenge. All right, which is cosecant, cosecant squared x bigger than m. That means that cosecant x is bigger than the positive square root of m, which means that sine of x is less than now, right? Taking the reciprocals of positive numbers. This is okay if everything is positive. Are you certain? Yes, I'm positive.
Why did you flip the sign there?
Basically, the reciprocal of small is large. So if the bigger thing is on the left here, and I take reciprocals, then the smaller thing is on the left.
Okay, I thought that was only when you divided by a negative.
Yeah, I know. It's one of those things that maybe you don't get enough practice with in pre-calc. So you get into here, right? Yeah, it's true also if you multiply both sides by a negative. But, so the crucial thing is that this is everything is positive here, right? So if you did have a negative, then this wouldn't work. But it's like, can I say 2 is less than 3, so 1/2 is more than 1/3, right? That's certainly true, right? Okay, so now what? Well, I kind of want to solve for x, right? So to solve this for x, you'd say arcsine. So x equals, well, actually, there's several values, right? The sign of a supplement is the same as the sign of the number, right? So I can say either arcsine of 1 over the square root of m, or the supplement of that, pi minus the arcsine of 1 over the square root of m. Or, you can add, I think, any multiple of pi, 2 pi to that, right? But in particular, we're sort of finding that we've got, so it's a little tricky, huh? So, you're gonna be solving. Okay, so so here's pi, here's negative pi then, and here's negative pi over 2, and so we got another asymptote here, and the function just repeats that same waveform over and over again, right? So if we have an m up here, then what should we choose delta to be? Well, you choose delta to be this arcsine 1 over square root of m. We were hoping for a break soon. I noticed that. Yeah. Okay. So let's finish up this problem, then we'll take a break. All right. So yeah, this is 2.4, the precise definition section, which a little bit of a trick. Okay. But yeah, it's building a firm foundation, folks. Okay. So I'm going to say that this allows me to say that if x is within arcsine of 1 over square root of m of 0, then f of x is greater than m. And I can just shift that over, right? So I'm going to say if x is within arcsine of 1 over the square root of m of pi, then you basically, so you got this interval delta around 0, which will put you above there, but the same is going to be true over here then, right? So if you're within that same distance of pi, then you're also above m, right? And so that's what this inequality is saying. If I'm within arcsine 1 over root m of pi, then this also follows, right? And we could look at that on the GeoGebra. Or sometimes you do this as scratch work, right? You work backwards from your goal towards what will get you to your goal by writing sort of sequence of equivalent inequalities, right? And then you say, well, look, I have the answer. If delta is arcsine 1 over root m, then I can show that f of x is greater than m, right? So if this is true, then we can say, yeah, that x minus pi is between arcsine of 1 over root m. There's no dogs allowed on campus? Just saying. Arcsine 1 over square root of m. So I think I can take the sign of all three members of this inequality since, yeah. So I can say, oh, I can add pi to all three members. That's what I want to do, right? So pi minus arcsine 1 over square root of m is less than x, is less than pi plus arcsine 1 over square root of m. Sorry, a little sloppy there. So then I kind of work this whole thing backwards, right? So what do? We got to sine x, right? So sine of this is going to be the same as I'm sorry, you can't see that. Sine of pi minus arcsine 1 over square root of m is going to be less than sine x. It's going to be less than sine of, I'm just going to put, what obviously goes there, goes there. All right. And then I can just drop the pi, right? Because the sign of the supplement is the same as the sign of the angle. So this is going to be 1 over, actually this would be negative 1 over square root of m. Sine x less than 1 over square root of m, right? And then I can take the reciprocal and square it, right? Yeah. And that'll be cosecant squared x. Yeah. And that's what I wanted. Oh, yeah, actually, I don't care about this end of it. Yeah, sorry. Maybe just scrap that whole left-hand side, right? Because we really just want the right-hand side. Oh, sorry. When I took the reciprocal, I should reverse the inequality. I forgot to do that, right? So when you take the reciprocal and square, and I guess when you're squaring, so the left side won't matter, right? Because you're squaring, right? So, yeah. Sorry, a little messy there, but gets the job done. And let me ask if there are any questions before we take a quick break. Did that? Oh, so if m equals 2,000, can we go back so we finish up the where is it here? So then what value of delta do I want? I want pi minus arc sine. Oh, I think I have to get pi from the, oh. Oh, round your answers down to 3 decimal places. I see. So what is, so I need to use a calculator here now, right? So for that, I'll go to the other Firefox thing, and turn this one off, and then go over to my calculator, which I guess I'm using GeoGebra for my calculator. Oh, that's not the one I want. How about here? Can I just compute? So m is 2,000, so I want pi minus arc sine of 1 divided by the square root of 2,000. And that's 3.11, right? So that's pretty close to pi, right? And it's just a little bit less than pi. I see. So what is the, yeah, what is the value of delta is their question, right? So let's answer their, make sure we answer their question, right? So their question is, what is delta? So delta is going to be arc sine of 1 over square root of 2,000. So maybe I'll compute that instead, right? Arc sine, oh, I can just write arc sine 1 over square root of 2,000. And I get, oh, they write it in degrees? We don't want degrees. So, I don't know. So I multiply this by pi divided by 180. Now it's still writing in degrees. Okay, but we know that we're converting from degrees to radians when we multiply by that. So pi should be 0.02236. And 0.022 3 decimal places. If it's 4,000, well, the square root of 4,000 is, well, we don't know what that is. Okay, so I'm just going to type in 4,000 here, and we get 0.158. Sorry, 0.0158. All right, let's try those and see. If they're wrong, we'll come back and fix them. Well, this one is right, but it didn't like that one. That's kind of peculiar, huh? Or was I just not close enough? You gotta be pretty close, I guess. 0.02236. You would think that, does it want the 36 then? Or maybe it doesn't like the fact that I'm putting in too many digits. Frickin' WebAssign. Where am I here? Okay, yeah. All right, just give it more digits than it needs and you'll be happy. Okay, was I good with these guys up here? Yeah, those were good, huh? Okay. All right, so take 10. We'll be back here at 7:20-ish. Any questions before we break? All right. We'll maybe do 1 or 2 more of these and then get on to 2.5, the continuity section, right? Which is where we sort of want to emphasize some of our work. Let this sink in. Don't fight it, you know. Just try to understand it. And when we get to continuity, I think you'll get a better sense of it. All right. So I'm going to pause the recording so we can take a short break. All right. So I don't know, some more of these. Let's see, where is it over here? Yeah. Prove that the limit of, root x as x approaches a is root a if a is greater than 0. Right, well, it has to be in the domain of the function, right? And we're going to use f of x minus f of a equals absolute value. Is that true? Well, maybe we'll walk through this one as well, just as a way of sort of wrapping this up, right? Because this one looks kind of hard. 8 is not so bad, especially if you follow the example like we did, right? And I think they're kind of walking you through with baby steps. So, so let's see. I left the cap off my pen. Oh, I need more paper. Okay, so this is WebAssign, like number 9 or something. Yeah, number 9. And we've got the limit as x approaches a of square root of x equals square root of a. Again, it's sort of obvious, right? Just substitution thing. But using the precise definition, we'd want to say that given any epsilon greater than 0, we can find the delta greater than 0. You know these abbreviations? This means for all. And this means there exists. This is sort of logic shorthand. This means such that. So for all epsilon greater than 0, there exists delta greater than 0 such that x minus a less than delta implies that f of x minus f of a is less than epsilon. That's the sort of shorthand. I know that looks like complete gobbledygook, right?
Yeah, could you not use that?
But this is, this is the way the pros do it. So I thought I'd just sort of roll that out there. So, so the challenge is this absolute value of, so we try to work backwards from the challenge, and they're giving us a little bit of a hint here that we can multiply this by square root of x plus square root of a over square, this trick again, the conjugate multiplier. So you multiply by 1 in that form. And since this is equal, these are both positive, it's equal to its absolute value. So we can take that as the absolute value of x minus the absolute value of a times the absolute value of x plus the absolute value of a, all divided by the absolute value of x plus the absolute value of a. And that comes out to the absolute value of x minus a over the absolute value of x plus the absolute value of a. Oh, look, there's our x minus a. That's kind of what we want, right? And so we want to have that be less than epsilon, right? Right, because that's what we started with, f of x minus f of a. We want f of x to be within epsilon of f of a. And that's what this is saying, right? And so that's my challenge. And how am I going to respond? Well, they actually, given epsilon, so I'm looking at the, basically I've just worked the hint there. So let me turn on the problem again. So we must find delta greater than 0. They give us an option of things. Yeah, greater than 0, such that this is less than epsilon whenever, and this should be a delta, right? That's just the definition. But this equals that is less than epsilon from the hint. Now, if we can find a positive constant c such that greater than or less than c. Well, if you look at I'm thinking about this. If you look at what we've got here, we're going to be, if we can make, yeah, so look back over here. So you want this to be greater than c, so its reciprocal is less than 1 over c.
Can't see what you're looking at.
Yeah, I'm looking at the page, the next little business here, right? So I think the clue to, so in fact, let me write that on my page. So, so if we can find, so they're saying if we can find C, so that square root of x plus square root of a, and the question is greater than c or less than c, and I think we want the reciprocal to be less than 1 over c. So we want this to be greater than c. Then 1 over square root of x plus square root of a is less than 1 over c, which is going to be equivalent to multiplying both sides by this positive number, right? So I'm just multiplying both sides by the absolute value of x minus a. Right, so again, it's this idea of if this positive number is bigger than that positive number, I'm assuming c is positive here, right? Then the reciprocal of that will be smaller than the reciprocal of the other, and we can then say that this is what we want this to be less than epsilon, right? So I'm going to say greater than, right? But it's the kind of thing where I get confused too, right? You just have to kind of think carefully about what's bigger than what and what's smaller than what. So let me put that back. I'm going to say, I think this should be a greater than, so that this is a less than. And we can make absolute value of that by taking this, the right side of this, by taking absolute value of x minus a less than CE. We can find this number by restricting x to lie somewhere in the interval centered at a. So there's sort of saying the distance from x to a is less than half of a? Okay, let me write that on my page. So they're kind of, you know, using baby steps with hints to walk you through this, right? So so we restrict x to lie in some interval centered at a. And in particular, the interval from, let's see, a minus a half, yeah, to a plus a half. Oh, I'm sorry. So it's going to lie in the interval from a over 2 to 3a over 2. That certainly is an interval containing a, right? Half of a is less than a, and half again more than a is bigger than a. So that's in an interval. So that is the absolute value of x minus a is less than a half, right? So the distance from x to a is less than half of a, right? So a is in the middle of this interval. A over 2 is 1/2 of a to the left, and 3a over 2 is 1/2 of a to the right. Okay. Then this is equivalent to saying, so you can always replace an absolute value inequality by a compound inequality like this, and then add, yeah, that's just what I had, right? Right. Hang on, folks. We'll see where we're going with this, right? So that implies that the square root of x plus the square root of a is less than the square root of half of a plus square root of a, right? Because the square root of x, I see. All right, this is a pretty sophisticated argument, and I think this is going to be less than, right? Because square root of x is bigger than the square root of half of a, right?
Professor?
Oh, so it's going the wrong way, isn't it? Go ahead.
No, it marked that wrong.
Yeah, right. Okay. Yeah, I was just realizing if you wanted to follow from this, right? So we're using this part of this and then saying, well, if half of a is less than x, then the square, so the square root function is monotonic. That means strictly increasing, right? Or it could be strictly decreasing. It would also mean monotonic. But in this case, square root of x is an increasing function. So if the left is less than the right, then the square root of the left is less than the square root of the right. Again, that's one of those not so obvious results, like, you know, taking reciprocals of positive numbers reverses the inequality, right? But so we have that if I replace x with this smaller quantity, I get a smaller quantity, right? So on the left side here, I've got square root of x, and instead of the square root of x, I have this smaller quantity, square root of 1/2 a, right? So this inequality goes that way. And so c equals, oh, okay. So that's what we want, right? Square root of x plus square root of a is then going to be bigger than that, which is going to be our value for c. Okay, so let's, is there something else they wanted? They don't, yeah. So I'm just going to write that in here and say, so choose, based on this, so choose c equal to, what was it again? Square root of half of a plus a. Maybe I should follow up with that last little bit. So square root of x plus square root of a is bigger than square root of half of a plus square root of a, right? So choose c equal to that. And can I just say, you know, factor out 1 over the square root of 2 plus 1 square root of a? Does that help to factor that out? Maybe not, huh? I suppose we could get a common denominator and say that's equal to square root of 2 plus 2 over 2 times a. Yeah. Okay. So thus, if x is within, and so we're going to have this c times epsilon, right? So there's a pull down menu for, let me go back to the, so this is going to be, well, that's obviously delta, right? Then this is greater than that. Also, if, yeah, and all of these, you know, you get 3 chances, right? And there's only 2 possible answers. So I suppose you could, the idea is to try to understand what's going on, right? Then this is less than that. All right, let me see if I got these right, and then we'll move on. Yeah, all green checks. All right. And I suppose I should finish up my argument over here, but now, what is the argument then? So let delta equal the minimum again, right? Of what 2 numbers do we have? Half of a, and that's if epsilon is huge. If epsilon is small enough, then we'll want to use this other value, which is square root of 2 plus 2 over 2. Oh, this should be square root of a here. Times epsilon, right? That's c times epsilon. And so then if x is within delta of a, you have 2 possibilities. Either x is within 1/2 of a, in which case we get our result, or x is within root 2 plus 2 over root 2 square root of a times epsilon, in which case it also works out, right? And this will be the smaller quantity. If epsilon is smaller, you'll probably want to choose this one, right? All right, that's pretty sophisticated stuff. So let's get down to some more brass tacks, or maybe that is the brass tacks, right? And it's a tax on T at this stage, since I've got my Russian caravan, and that's pretty strong stuff. Black tea. I'm going to be up all night. No, it doesn't do that to me. Okay, so what am I doing? I'm going to the other Firefox, right? Which is this one. Oh, okay. So what happened to the first one? Okay. And we want to then get to, oh, they've disengaged me from this one. So, okay, how about webassign.net and log in. And go to the ebook. We want to get in 2.5. And for that, we'll go here and then choose, here. What happened? Did I click on the wrong thing? Oh, mercy. Your request got an error. Kind of unfriendly sometimes. You ever get that feeling? Okay, I want to go to the ebook. It's like they don't want to be hacked or something, you know? Chapter 2, it'll take me to 2.4. I don't want to be there, so I click on this. And 2.5, continuity of a function. And here we get properties of continuous function, and we get the intermediate value theorem. This is sort of a biggie. And then we do have a bunch of other sections. So let's get the definition of continuity, right? A function f is continuous at a number a. Where are we here? Oh, so they're going to have this guy explaining something. If the limit exists and is equal to the value of the function at the point. So if it doesn't have a jump or a discontinuity or a removable discontinuity, so this basically means it's unbroken at that point. So this is continuity at a point. So it doesn't have to be continuous on the interval. It just has to be continuous at the point. So this is another subtlety, which, in fact, you can have a function which is only continuous at A and not in any neighborhood of A. Crazy, huh? But that's sort of the flip side of the limit existing at the value. It doesn't matter what the value of the point is. Here, it does matter what the value of the point is, right? It's got to be f of A. F of A has got to be equal to the limit, is what I mean to say. Okay, so notice it requires three things. Oh, okay. So f of A is defined, the limit exists, and the limit is equal to f of A. Okay, so you can think of that as three different things. So here's a function which is continuous at A, and so it does just what you'd expect. I mean, it's well behaved. So continuity essentially means well behaved, right? So it looks like there's a discontinuity when A equals 1 because the function has a break there. The official reason is that f of 1 is not defined, right? In fact, the limit exists, but it's not equal to the value of the function because the function doesn't have a value there. Here, the limit from the left is different. At 3, the limit from the left is different from the limit from the right. So that's a jump discontinuity. Here, the limit from the left equals the limit from the right, but they don't equal the value of the function. F of 5 is way up here somewhere, right? And so that's a removable discontinuity. We say it's removable because we could just move this point back to where f of 5 looks like it should be, and then it would be continuous at that point. All right, so they give you a bunch of examples. And yeah. And so here's a step function, has a sequence of discontinuities. Vertical asymptote, here's a removable discontinuity. So a function is continuous from the right if the right-handed limit exists, and it's continuous from the right and equals the value of the function, right? It's continuous from the left if the left-handed limit exists and is equal to the value of the function. All right, and here's your, are you familiar with this function? This is the integer function, or it's sometimes called the greatest integer function, after Muhammad Ali, who was the greatest. No, this is the largest x less than or equal, the largest integer less than or equal to x. Yeah. And it's continuous from the right, but discontinuous from the left because the limit from the right at an integer n, right, is just going to be equal to n, right? Because n is the largest integer less than or equal to n. But from the other side, you know, you're always going to have values less than n, so it's always going to be, well, as you get between n and n minus 1 and n, the greatest integer function will have the value n minus 1 until you get to n. But on the way there from the left, the greatest integer function is always going to be n minus 1. So that, and you can see that from the graph. So here's a new definition: continuous on an interval. If it's continuous at every number in the interval, we understand that continuous at the endpoint to mean continuous from the right and continuous from the left. Right, so if it's continuous from the right at the left endpoint, then it's continuous on the closed interval. Oh, and continuous from the left at the right endpoint. So they have, is this another example? So this function is continuous on the closed interval, including its endpoints, right? Because f of -1 is going to be 1, and f of +1 is going to be 1. And they're in the domain of the function, and the limit equals those values. So it's continuous on the closed interval from -1 to 1. And let's get on to the intermediate value theorem. Are we ready? Oh, properties. If f and g are continuous on some interval or at some point, and then so is the sum, so is the difference, so is a constant times it. So is the product, and so is the quotient, provided the denominator doesn't go to 0. And they give you some proofs of these things. By limit law 1, we can just say the limit of the sum is the sum of the limits, and then use the substitution theorem, and we have that, what we want. Any polynomial is continuous everywhere. Polynomials are well behaved, right? Any rational function is continuous wherever it is defined. So it's continuous on its entire domain, right? In fact, we say that a function that's continuous on its domain is a continuous function, even if the domain is not all real numbers. Okay, well, we should probably look at a bunch of exercises so we can practice working with these things. So here's a rational function. It's continuous on its domain, right? And the domain does not include 5/3, but every other number. Okay, so the trig functions are continuous everywhere except for the tangent function is continuous on its domain, but does not include, you know, these pi/2 and 3pi/2, odd multiples of pi/2. So the following types of functions are continuous at every number in their domains: polynomials, rationals, root functions, trig functions, inverse trig functions, exponential, like a lot of our favorite functions are continuous over their entire domain. The exception being the integer function, the greatest integer function we just talked about, right? That's not continuous on its entire domain. Inverse trig functions are reviewed in section 1.5. Yeah, we did that. Okay, so they have a bunch of examples. Here's a theorem. This is a biggie. If f is continuous at b and the limit as x approaches a of g of x is equal to b, then the limit of the compound function f of g of x is equal to f of b. In other words, you can take the limit inside the compounding if the outer function well, let's say if the limit of the inner function exists and the outer function is continuous at that point. So we saw special cases of that for like the power function and the root function. Those are examples of that. You know, the power of some other function or the root of some other function, those are compound functions. I suppose we should get down to doing some exercises, but first we need the intermediate value theorem. If G is, this is not that, G is continuous at A and F is continuous at G of A, then the compound function given by that is continuous at A. Isn't that what we just did? They give you a little proof of that. And let's get on. I think now we get the intermediate value theorem. So this is a very intuitive theorem, but I don't think we have to notice what they say here. They don't even provide the proof in the appendix. Right? Proof is found in more advanced books on calculus. Wow. Must be pretty complicated, huh? Yeah, it's not so bad. You may even want to do it. But the statement of the theorem is pretty clear and intuitive. Suppose f is continuous on a closed interval, which includes its endpoints, right, a and b, and let n be any number between f of a and f of b, where f of a is not equal to f of b, right? Otherwise, there wouldn't be numbers in between. Then there exists a number c on the interior of the interval such that f of c equals f of n. And they draw you a picture here, right? So here's a continuous function on the interval from a, b. We're given a number n between f of a and f of b. We're guaranteed to find some value. So this is an existence theorem, right? It guarantees the existence of c in the interval from a, b, so that f of c is equal to this given value n between f of a and f of b. And the idea is, you know, imagine trying to draw a curve between this point and that point that's unbroken and doesn't cross this horizontal line, y equals n, right? You can't do it. You might try to go around, but you know, then you would violate the one-to-oneness, right? Yeah. You know, you put a break, but then it's not continuous, right? Show that there, so the applications are particularly interesting. So that there is a solution of this equation between 1 and 2. So you have to find, you know, value. So this is continuous everywhere, this function on the left side of this equation. And at 1, this is negative. Yeah, 7 minus 8 is negative. At 2, it's going to be positive. So since f of 1 is negative and f of 2 is positive, and 0 is between any negative and positive, there's going to be some solution to this equation in the interval from 1 to 2. Do they draw a graph of that? Yeah, they do kind of, right? All right. And do we then get to the exercises? Yes. So let's work on a couple of those and then maybe see if there's some WebAssign that's interesting. How about number 1? Start at number 1 and keep going until you reach the end. And write an equation that expresses the fact that a function f is continuous at the number 4, while the limit as x approaches 4 is equal to f of 4. There you go, right? 2, if f is continuous everywhere, what can you say about its graph? It's an unbroken curve throughout, right? You can't say it's smooth, right? It could have sharp points and stuff, but there's no break. So you can draw the graph without ever lifting your pencil from the paper. From the given graph f, state the numbers at which f is discontinuous and explain why. Well, it's discontinuous at -4 because f of -4 is not defined. It's discontinuous at -2 because the limit from the left is not equal to the limit from the right, so the limit does not exist. it is continuous at 0, right? So here's a sharp point, but that's not a break in continuity, right? It's a place where it's not smooth, but it is continuous. Same problem at 2 as at -2, and at 4 essentially, right? Although it looks like maybe there's a vertical asymptote as you approach from the left. Hard to say, right? And yeah, okay, so shall we take a look at a few more of these? How about here they want in 7, 8, 9, and 10, graph a function f that is defined on R and continuous except for the stated discontinuities. All right. So I'm thinking, let's work one of these here. You know, how many are there? There's 76, one for every trombone in the big parade. Oh, we're back to the big parade. So here we have a function, let's say number 24, which has one formula for x not equal to 3 and is defined to be 6 if f equals 3. So does that factor? I'll bet you it does. All right. Shall we write this one up? So I'm going to go here and put this up. So here's my function, right? So this is 2.5, number 24. And we're looking at piecewise function. F of x equals 2x squared minus 5x minus 3 over x minus 3. Does that factor? X minus 3, you'd have to have 2x plus 1. Yeah, that's it, huh? So this is 2x plus 1 over times x minus 3 over x minus 3. And it's going to be 6 if x equals 3. So this is you know, if x is not equal to 3, but I wanted to factor it here, right? So you can see, yeah, so 6 is not on 2x plus 1, right? So another way of defining this function would be to say f of x is equal to 2x plus 1 if x is not equal to 3, and x is equal to 6 if x equals 3. So what do we have? We have a line with slope 2 passing through y-intercept 1. Oh, we want to get out to 3. I'm just going to do that. I can do that, huh? 2. These are perfectly evenly spaced hash marks. And we have a slope of 2, right? So we're going to go up 2 here and up 2 there and up another 2 there. And we see that we have this curve, straight line, which is going to be everything except at 3. Sorry, it didn't quite fit on the curve, right? Where what happens, instead of it being 7, it's 6. So this is going to be the 0.36, just below 7 there, right? And what's their question about this? Clearly, that's a removable discontinuity, right? What is the question? Explain why the function is discontinuous at the given number and sketch a graph. Okay, so I did the sketching of a graph without even reading the prompt. You know, I could have had a better graph. Don't forget to label your axes when you sketch a graph and to scale your axes and to make perfectly evenly spaced hash marks. And, you know, so why is it discontinuous? The limit as x approaches 3 of f of x is equal to 7, which is not equal to f of 3. which is 6, right? So the limit exists, but it's not equal to the value of the function at the point, so that's a discontinuity. Right, I'm sort of monitoring the chat now. Did you reload the page? Yeah, multiple times. Oh, so this is Zoe. Only shows one on the main menu, but it shows both when you get into current assignments. Oh, so did something go wrong with the 2.4s? Try to open one, he deleted, doesn't actually work. Huh, wonder why it's shown. It was just a visual problem? Okay, so they're working now? Let me know if you have trouble. Okay, let me know if you have trouble and I can see about that. Okay, so that was 24. How about 36, since that looks like a nice, I'm gonna just write it here since, so here's number 36, which is, what are the instructions? Use continuity to evaluate the limit. Okay. And this is the limit as theta goes to pi over 2 from the left and the right, right? That's sort of implicit. Sine of tangent of cosine of theta. So this is a composition function, right? And it's a composition of continuous functions. So if we were to substitute pi over 2 for theta, well, cosine of pi over 2 is 0. That's a place where tangent is continuous. Tangent of 0 is 0, and sine of 0 is 0, right? So I don't know. So this is going to be, if you really wanted to be pedantic about this, you'd say this is the sine of the limit as theta goes to pi over 2 of the tangent of cosine of theta. Sorry, that barely fit in there. Maybe I need to start writing farther to the left. We measure up. Or we measure left. So then we'd say this is the sine, right? Because everything is well behaved, right? So you can keep taking the limit inside, right? And then you can compute the limit of cosine. So that's going to be 0, I believe, right? Yeah. Which is sine of 0, which is 0. That was 36. How about 48? We're going by 12s. Find the values of A and B that make F continuous everywhere. So this is number 48. Find the values of A and B that make, and this, yeah. Here's our function. X squared minus 4 over x minus 2 if x is less than 2. Well, again, that factors and reduces, right? And it's going to be ax squared plus, or minus, sorry, bx plus 3. I don't have an eraser for my Sharpie. If x is between 2 and 3, strictly less than 3, sorry. And 2x minus a plus 2x minus a plus b if x is greater than or equal to 3. Okay, well, let's make this a little quiz with groups because we have 12 minutes left and that ought to be enough time. So I will go to here, or no. Yeah, that'll work. Here, and I'm going to add a little discussion quiz with groups, and everybody can respond. So this is going to be a little discussion. And it's a new topic. This is 2.5. And I'll come around in kibitz if you need kibitz in, right? 2.5, number 48. And don't in debt. So I'm going to add this item. And I'm going to publish it. I'm going to edit it. Oh, I think I can do it here. I just click on it and then edit that. And so do I want to? Yeah. So solve. I'm not going to try to type it up here because I don't have time, but 2.5, number 48, maybe later I'll try to figure out how to typeset that. Notice that I don't get math type. I thought I'd installed that. It's a little annoying. And respond to this prompt with your solution. Include the whys and wherefores of how you arrive at your solution. Okay, and then we're going to say this is graded with some 5 points. Is not too high stakes, is it? And let's make it due by this time tomorrow. You don't have to finish it tonight is what I'm saying, but I'm going to give you some time to get started on it. You could probably finish it. I mean, it's not a terribly difficult problem, right? You just use the definition. This gives you a chance to use the definition, right? Okay, and so then any questions before we break into groups?
Could you make the all of the due dates what they're actually going to be so we don't have to kind of guess when we have to do our work for the homework?
Right. So that's on WebAssign, right? So that they're wrong now, is that it?
Right now, all of the homework is due this Wednesday.
Okay, I see. Yeah, the new ones I just assigned, right? Because I hadn't fussed with that yet. Okay, yeah, I'll extend those out. I can also, respond to requests for that if you like. So how many rooms shall we have? Well, there's 22, it says 23. So let's say that's 6 rooms will get us, mostly 4s. I suppose if we went to 7 rooms, well, that'll be fine, 6 rooms, okay? So I'm going to create, so it'll be 3 to 4 participants to the rooms. And you're now invited to go there. And I'll hang out here if you have some questions before jumping in, or maybe just want to jump in there and start, because I think you'll lose my audio when you jump in. So, except I will be coming around to Kibitz. All right. You waiting for something, Oscar? There he is. Okay. How about Alejandro? Breakout room 2. All right. Called you out. I think that's...
I got disconnected during when we got put in the groups.
Oh, is this Travis? Okay. I'm going to assign you to room 4.
Okay.
Dalton, you need help, or you're supposed to be in room 1?
Oh yeah, I know, but no one was even talking. Everyone's screen was black, so I just came back here.
Oh, okay. How you
Just to
doing?
wait.
You working on stuff?
I'm doing okay. I was already working on the 2.4 homework, and then it swapped to a new homework, so now I have to
Oh,
restart on
sorry
that.
about that. Yeah, I pulled the rug out from under you, but there are a lot fewer problems on the new one.
Yeah, no, I noticed that. That was nice.
Okay. So that's
about
some
that.
compensation.
Yeah.
Sorry about that.
No, it's all good.
Yeah, I'm still finding my ropes on WebAssign.
I'm a little bit confused with some of the stuff that we went over today with I think it was in 2.4. It was here, I'll try and find one of the questions. Or it was about the one we had to do limit laws with the precise definition. Are we gonna have to do that on tests?
Yeah, that might be a problem. It's not going to be heavily emphasized, but since we spent some time on it, it doesn't hurt to, put a problem like that.
Okay.
It's the basic foundation of calculus.
Yeah.
Yeah. All right, so for this one, you just got a system of 2 equations and 2 unknowns, huh? All right, let me jump in and see how you guys are doing there.
Hello? Bro, what's going on?
I think we're just waiting for him to come back on. But it said he was the host and he
Yeah,
disappeared.
I know. It saves the host and then it doesn't see it's like it's on here. You didn't join the group or the
Yeah,
specific
he would have ended it if he. I don't know, honestly.
I don't know, but can he put us all back too? I don't know. It's just weird. I don't know. And is he gonna like continue the class like over 8:30, or is he just gonna like end it?
No, I think he was gonna end it, but I feel like he was gonna come back and help us answer it. But at this point, I have no idea.
Maybe he's talking to the group like in another we call meeting or whatever.
Probably.
I don't know. Whatever.
participants.
Professor, is the answer negative infinity to infinity?
Oh, it's the answer is the values of A and B that make it continuous. All right. So
Yeah.
what's A and what's B? That's the question.
So those have specific values then.
Yeah. Right. Yeah.
Yeah.
Did you see how to get them?
No, I'll figure it out.
Okay.